So, yesterday we are looking at the description of point defect model, right, and there are 3 generations in it. They are classified as 1, 2 and 3, and after that we will see few other variations of that. So, based on what we have seen, we have a metal here, we have a film and we have a electrolyte here. We have looked at a total of 7 reactions. Okay. So, on one side cation vacancies are created, cation vacancies are denoted by plus here, actually it is vacancy, and they are created on solution side and they are consumed on the metal film interface. Anion vacancies are created on the metal film interface and they are consumed in the film solution interface. Interstitials, cation interstitials are formed here, I is formed here and I is consumed here. Okay. And the 7th reaction is dissolution of this. It can be a chemical reaction, it can be an electrochemical reaction depending on whether the cation oxidation state in the film and cation oxidation state in the solution, they are different or the same. If they are different, then you have an oxidative or electrochemical reaction. If they are the same, it is just a chemical dissolution, but that is just film dissolving into this. So, these are total 7 reactions. So, any of this can be rate limiting. We have not yet considered the movement of electrons or holes through this, but that also should be considered. If number of electrons that are formed or holes that are formed, if we have many electrons, if it is basically an electronic conductor, that will carry most of the current. Diffusion of the ions will not carry that much current, diffusion of the vacancies will not carry that much current. Basically, it will appear like a resistor. When it is not a good electronic conductor, only then we have this issue, or number of electrons are very few or number of holes are very few. Okay. Then we have this vacancies going through this or interstitial going through this for conduction. Okay. If you look at the current through this, through the film, I will have current because of electrons, I will have current possibly because of holes, we will have current because of the movement of metal, I am sorry, metal vacancy or cation vacancy, we will have current because of movement of anion vacancy, and we will have current because of movement of interstitials. In case the anion vacancy movement is the most dominant mechanism, the film will appear as a N type semiconductor. Okay. And an example is tungsten with tungsten oxide formed on the surface. So, it is obviously it means that electronic conduction, hole conduction, they are all much smaller compared to this. Okay. Cation vacancy conduction is not that high, cation interstitial conduction is not that high, the major current carrier is the anion vacancy. In case the cation vacancy is dominant or transport of cation vacancy is dominant, right, the film will be a p type semiconductor, and an example is nickel oxide. And if cation interstitials movement is dominant, then again it will appear as an N type. Okay. So, depending on which movement is dominant, it is going to appear as an N type or p type semiconductor. If hole is dominant, it is going to appear as a p type, but then the conductivity of that film is going to be very high. If the p type behavior arises from the cation vacancy transmission, then that conductivity will be poorer. If it is because of holes, the hole will move fast, their mobility is high compared to the vacancy movement. So, that will also appear as a p type semiconductor, but then it will have much better conductivity. In general, current can be carried by any phi of this or all phi of these pathways. Since they are occurring in parallel, we will have to add the admittance to get the net admittance. Okay. So, we will write the film admittance is going to be the admittance due to the flow of electrons, flow of holes, cation vacancy, anion vacancy and cation interstitial. Typically, one of them will be a low value, if current is high, the impedance is going to be low, admittance is going to be high. If I say this cation vacancy is the dominant mechanism, this will be a large number, this will be a small number, this is going to be a large number, and we can neglect the remaining. If they are comparable, then you have to use all of them together. Okay. I am still giving you only a qualitative view of this, I am not showing the derivation. Okay. And I will also just introduce how these equations are developed, but I am not going to go through the full development. The rate at which the oxygen or anion vacancies are generated, okay, not the rate at which they are generated, the concentration of anion vacancies at the metal film interface, concentration of anion vacancies at the film solution interface, they are given by these equations, where n is the Avogadro number. This omega here, it is not the ohm, it is not the unit of resistance, instead it is a molar volume of oxide. Alpha here is the polarizability of the film solution interface. Okay. Theta 1 is a constant, likewise theta 2 is a constant, and potential here is given by E, which is both DC and AC together. Basically, there are expressions to calculate the concentration of anion vacancies, concentration of cation vacancies, diffusivity, estimation of diffusivity is, you can put a diffusivity term there and then you can calculate based on fitting it to the experimental data, but it is possible to develop the equations while accounting for the presence of electric field and accounting for the fact that these are charged entities. So, essentially we are using an equation which is similar to Fick's law, and this has to be corrected, but this accounts for the fact that these entities are charged. Okay. Epsilon is the field strength, I think I missed the Q here. Q is the charge of the vacancy or interstitial. F of course is Faraday constant, RT we know all these values, temperature and then universal gas constant. So, Nernst Planck equation is used when we have movement diffusion. If the entities are charged, we have diffusion because of concentration gradient, we have diffusion or movement because of electric field, and these two together accounting for both the concentration gradient and the electric field, of course in one dimension. Okay.
So, there is no influence of mass on this equation?
Diffusivity, why would the mass come there?
Diffusivity is a characteristic.
Yeah, but why would mass come there?
I think like if it's more little diffuse, it will go slower.
If it's, see, you are saying if it's larger volume, it may go slowly, that means diffusivity will be smaller number. We are basically using the term diffusivity here, capital D here, to account for whatever is possible. This D is in this crystal or this amorphous film, in this medium. Diffusivity in water is going to be different for the same species. It is going to be ion, of course, surrounded by hydration sheet. So, diffusivity here obviously it means diffusivity in this medium. So, you can understand why this is called point defect model, right. We have a lattice in which vacancies are present, and these vacancies are of course called defects, and because it is present in the lattice, these are called point defects, and since that is used to explain the conductivity and the impedance, this is called point defect model. Okay. Potential drop across this interface. So, when we apply potential, normally in a metal solution interface, we would say potential drop occurs very close to the double layer, not very close to the, its potential drop occurs across the double layer, and if solution resistance is negligible, it is going to be more or less constant potential in the solution, and in the reference electrode again there is going to be a potential drop. But whenever we vary the potential using the potentiostat, the change occurs only here because the reference electrode potential drop is a fixed number. If solution resistance is significant, then depending on the current value, you may have a potential drop in the solution also. Now, when you have a film, the double layer occurs here, there is a potential drop. In addition, there is a potential drop across this film, and in addition there is a possible potential drop across the metal film interface. Okay. So, what we apply is from this location to other location in the reference electrode, and there we assume it is fixed anyway. In these calculations we are going to assume solution resistance is not that high, the resistance due to the film is going to be usually much larger. When we look at the potential drop across the electrode in, and if it is measured with respect to particular reference electrode, we have to consider 1, 2, 3 potential drops. Potential drop across the film solution interface depends on the pH, it is going to be linearly related to the pH. Okay. And of course, the applied potential, if you apply certain potential, part of it will occur here, part of it will occur here, and part of it will occur here. How much occurs here depends on the potential and the applied potential. So, I am sorry, depends on the pH and the applied potential. How much occurs here basically depends on the thickness of the film and of course, what we apply. How much occurs here is going to be E metal film is going to be basically E applied minus E film solution. Okay. Normally, in the previous example where we just had a metal, whatever we apply, if we say solution resistance is negligible, we are going to say this is just occurring across this with respect to this reference electrode. Whatever we apply is applied across the interface, that is how we have done the calculation. Okay. Now, we are going to say whatever we applied is split into 3, one of them is going to depend on pH, another is going to depend on the film thickness. So, this potential drop across the metal film interface is going to depend on both pH and the film thickness, and naturally dependent on how much we are applying, how much potential we are applying. Now, when you solve these equations, you get a result which is somewhat similar to Warburg impedance. Okay. It might look similar to a semi-infinite Warburg impedance, it might look similar to a bounded Warburg impedance. You can visualize that the diffusivity is going to be much smaller than the diffusivity of a species in solution, right. Or another way of looking at that is to say that the film thickness is going to be very high when you compare it with the diffusivity. You can't compare it directly with the diffusivity, the units are different, but you can visualize if the diffusivity is small or film is large, they will have similar effect. So, a lot of times it will appear similar to a semi-infinite Warburg impedance. Okay. This model is able to predict successfully for different types of metal solution interface or film solution interface, how the film thickness varies with the potential. Okay. If you have higher potential, you would normally expect a thicker oxide, but it is not going to necessarily vary linearly, because dissolution rate, formation by different mechanisms, all these things have to be considered. This is able to predict for many cases the thickness variation with respect to potential, impedance response for different films, and there is a phenomena called pitting corrosion. If you have a solution, a metal here with the film on top, right, uniform corrosion is where everywhere it is dissolving at some rate. Pitting corrosion usually refers to the case where if you look at the surface, there are clear pits. That means it is localized, it occurs in some locations. Of course, it is dangerous because it is attacking the material and it typically goes below and keeps corroding more. So, on the surface you will see few points, some corrosion, but actually corrosion is, it can occur deeper. If you see full corrosion everywhere, it is not such a problem, meaning it is a problem, but you are prepared for that. If you see rust everywhere, you know it is getting weaker. If it is few pits, you think everything is okay unless you look very carefully, it looks like surface is okay, but actually the material is getting weakened. Okay. And pitting corrosion is seen usually when you have chloride ions present. It happens when you have chloride ions present. It takes some time for the pitting corrosion to occur, meaning there is a initial period where nothing is happening. Nothing is happening meaning where you do not see any pits. I do not mean to say nothing happens, I mean nothing is seen. There is a incubation period where nothing is visible, and after that pitting corrosion occurs. These are experimental observations, and this model is able to explain why that can happen. Okay. Let us see if I have prepared a slide for that, if not I will describe it here, okay, maybe not. So, I will just describe qualitatively what this says. So, in this model, pitting corrosion happens when chloride ions come here, metal vacancies that are generated here, right, the rate of formation of metal vacancies increases, cation vacancies, I should not say metal vacancies, I mean cation vacancies. Because of that, cation vacancies move here, that is to say metal forms metal ion and moves this way. The cation vacancies accumulate here. Normally, if you do not have chloride, of course, even then cation vacancies will form here and cation vacancies will come here and they will be taken up by the metal and they will diffuse inside and go. Okay. If you have lot of cation vacancies here and the rate of consumption of the cation vacancy by metal is not keeping up with the rate of arrival of the cation vacancies, you will have void formation. So, the corrosion does not occur here, meaning it is not becoming a void here, it is actually becoming a void at the film solution interface, and that happens only in some locations, meaning where chloride ion accelerates the formation of cation vacancies. It is not occurring throughout this. It may accelerate in some specific locations where the grain boundaries meet, or certain cases where it is easier for it to accelerate. In other places, it may accelerate to some level, but not to a large level, only in certain locations because of some weakness there meaning it may be a grain boundary, or it may have some other defect already present. It accelerates and cation vacancies which are formed here will move by diffusion and it creates a void at the metal film interface, and then the void grows. So, the void actually grows from inside the film. It is not the dissolution occurs here more rapidly on the film surface, film solutions interface. That also explains why it takes some time, because the vacancies have to accumulate to some level. So, it explains why that incubation time is seen experimentally. Some theories were there before which said chloride ion is diffusing in, coming here and attacking it, but it is not likely for a large anion to move through a film. It can come in and get incorporated and then it can go by jump, that is possible, but one chloride ion coming here, few chloride ions coming here will not cause such a void, whereas chloride ions sitting here, but accelerating this formation of cation vacancy will definitely cause this issue. Okay. Typically, pitting is seen when you have chloride or fluoride. Fluoride is not common in environment, chloride is common in the marine environment. So, the first level of model, actually cation interstitials were not used, although I described it with 7 equations. Okay. They had 5 equations. There were no cation vacancy or cation interstitial formation and consumption, but for completion sake I wanted to introduce with the proper model. Second level is to recognize the film that is seen is actually not uniform all the time. most of the time it contains two layers. One is a thin layer, but it offers protection, it is called barrier layer. Second is an outer layer, it can be porous, and that is formed when this cation interstitial as well as the dissolution of the film releases cations here. They can interact with the solution species and form a precipitate. This can be very thick compared to this film. This can be few nanometers, this can be in microns. So, I kind of drawn it like this. By the way, everywhere I am not drawing really per scale. When I show a metal and then a film, it is just a pictorial representation, it does not mean you have a thick film there, even in the previous examples. Right. So, in this case inner barrier offers protection, and this layer grows into the metal, and when the cations are ejected out, they react with the solution species, which means this is likely to be porous. Outer layer may be porous, it may contain solution and may be very thick compared to this inner layer, which also means when you analyze it later, if you take this, put it under vacuum, one technique that is used to measure the concentration on the surface or identify the species is called XPS. Okay. You can find out the concentration of various species on the top, including the oxidation state, by using this. Depending on what angle you are using for measurement, you can get few nanometers or even 1 nanometer thickness layer can be probed, and then what people do is remove the layer nanometer by nanometer by a technique called sputtering. Okay. So, which means you can monitor the film composition as you go down. Here it means as you go down from the outside to the, as you go down from outside to the inside, what is the composition. But if this film is 1 nanometer thick and if your measurement is let us say 5 nanometer or 10 nanometer thickness, you might quickly miss this. It may just sputter through this and quickly pass through this. So, it may not be that easy to detect it using other techniques. Barrier layer can be very thin, it can offer protection, but if you have a thick outer layer, you may not be able to see it that easily by other techniques. Okay. You may find the film to be porous. If you are using other technique, you might say, I think the film is porous, but it may offer a good protection, not because that film is offering protection, because the very thin film just on the surface is offering protection. Okay. Then a third generation is to recognize sometimes the barrier layer can actually offer protection, not barrier layer, I mean the outer layer can offer protection. Okay. If it is very resistive, like materials like tungsten, titanium, zirconium, they have a thin film which offers protection, and even there if you consider the quality of the film changes with distance, you can say one is an inner film, one is an outer film. The outer film itself is very resistive, that it is protecting this material. Okay. By the way, everywhere in this model or even in what others are presented, we assume that the metal is a, it is a single metal, it is not an alloy, the material is a single metal. If you alloy, the composition will vary. Even here the same metal, the composition can vary across this, you may have less defects, more defects at different locations, that is one. What I have not described is a metal like titanium can be present in Ta3 plus, Ta4 plus, multiple oxidation states, becomes more complex, therefore, we are restricting ourselves to a simpler case of Ta becoming Ta4 plus, tantalum becoming tantalum pentoxide, that is it, although it can actually exist in other oxidation states also. And an example, right, if you have zirconium immersed in lithium hydroxide and boron hydroxide, this is used for I think nuclear, in some nuclear facility, I am not very sure. Okay. Yeah, I think it is used in nuclear facility, okay. High temperature, high pressure for certain types of nuclear reactors. If you look at the impedance, this is how it appears. The main feature that I want you to see is it appears with a Warburg like signature at the low frequency. It has tens of kilo ohms centimeter square, right, impedance at the low frequency, sometimes mega ohms in that range. but the characteristic signature is either this or the film thickness is very small and diffusivity is moderate. You can have something like a similar to a finite Warburg impedance, not exactly described by the finite Warburg impedance, but somewhat similar to that. Okay. There is a variation to this that is proposed by Martin Boinov. Could not get a better picture. So, whatever I got I put here. In the point defect model, what is used is Nernst-Planck equation, which uses which assumes that the medium is continuous, meaning it is used for solution. If a charged species moves in solution, we use Nernst-Planck equation to describe the movement. Whereas, if we have discrete locations, which is what is realistic in a crystal, okay, the equations that are used to describe the movement of charged species in discrete location is little different. Okay. It is called Frommel and Cook equation. That is used instead of Nernst-Planck equation, it gives you a slightly different expression. Other thing is the accumulation of ions in this, right. You can have cation vacancies on one location, anion vacancies accumulating in another location. Accumulating meaning the species concentration is not uniform. If it is uniform, you will not have diffusion. It is formed in one location and consumed in the other side. For cation vacancies, it is formed here, consumed here. Anion vacancies are formed here, consumed here. So, we assume the concentration gradient is going to look like this, correct. It may or may not be linear, we probably assume it is linear, but you can say concentration of anion vacancy is going to be higher here and lower here. Cation vacancy is going to be higher here and lower here. If cation vacancies is higher here and anion vacancies are higher here, naturally the film is not going to be neutral everywhere. We are going to assume it is charged differently at different locations. And when you apply sinusoidal potential, these charges will also move or will tend to move, that is one. Second, if you really think about it, if this is the potential, this is the film thickness, okay. Under anodic potential, when you give higher potential, oxidation is more likely to occur. So, metal will form a metal oxide. So, if you go to larger potential, you will expect a thicker oxide in the passivation region. So, if I apply sinusoidal potential, I am increasing, coming back to this, decreasing and coming back to this. So, I can also expect the film thickness will increase, come back to this original, decrease and come back to the original, provided it happens at a very slow rate. The potential variation happens at a very slow rate. So, if I go to low frequency, it is possible that the film thickness varies with potential. Normally, when we apply sinusoidal potential, we say this is the DC potential, this is the film thickness. I cause a perturbation, I apply an AC, I am assuming the rate of movement of the electrons, holes, vacancies will vary. I normally do not assume that the film thickness will vary, but here you can take the variation of film thickness into account. We normally think it is very small, but here this model says that it may not be small. The presence of the charge, the distribution of charge at various locations, right, it is not uniform, it is non-uniform, that along with this variation of thickness of this film, okay, those are all included in this model, and this model predicts that at mid frequencies you will get an inductive loop. In some cases that is seen, the point defect model without these variations or changes does not predict a mid frequency inductance, but when experimentally you see this, so this is an example. So, niobium is like tantalum, okay. In acidic fluoride medium, it gives a spectrum which goes like this, not really vertically, it is little bit to the right side, and 2 volts I think with respect to open circuit potential, or I do not remember what it is with respect to, but this is definitely in the region where it is passivated, potential and current passivated, and it is either here or in the region where it is more or less flat current here. You see an inductive loop and you see a vertical line going up.
What do you mean by the passivated region? You get this.
Okay. When you put niobium in acidic fluoride medium, meaning HF based liquid, it can be with buffer, without buffer, it will dissolve. When you do not apply any potential, it will dissolve at a slow rate, depending on the concentration. I should not say slow rate, depending on the concentration, it will dissolve at a higher rate or lower rate. If I give positive potential, the dissolution rate will increase up to some level, the current will increase up to some level. Okay. Oxide formation rate will increase. Let us say that the net rate of dissolution in this particular solution is at this level. I am just going to draw in the air. Okay. Metal converts to oxide, oxide is dissolving into the liquid. Okay. The rate of formation of metal may be slow. I am sorry, rate of formation of metal oxide, metal converting to metal oxide may be low. If I apply more and more positive potential, I am increasing the rate at which metal oxide is formed, and when it is formed, it is also removed. When I apply large potential, the rate of formation of metal oxide is more than the rate of dissolution. Then an oxide will form. Now, the metal oxide interface will have a lower potential. I apply this much potential, but certain amount of potential is dropped in the film, because there is a film present here, significant amount of film present here. Now, the remaining potential is going to form this. Now, the dissolution rate will decrease, because the rate of formation of metal now is not that much. I am sorry, rate of formation of metal oxide is not that much. Okay. So, what happens is, when you give more and more potential, the dissolution rate increases up to some level and then decreases further. Then it remains more or less flat, it actually increases slightly, and after that it will again increase when you apply so much potential that the cations will really pass through the film and come out. It does not need the metal to form oxide, and then only the oxide dissolution is important. If cation comes out here and goes out, that also causes dissolution. So, this is called transpassive dissolution. Beyond passivation, you can have further dissolution if you go to that potential. Now, we have seen earlier that the slope of this curve gives us the low frequency impedance, correct. Meaning, if this slope is positive, I expect the low frequency impedance to come and end here. It may come and end like this, it may come and end like this, it may do whatever and then come, but it has to end somewhere there. If the slope is negative, it will end at this location, negative side, and of course, I can get quantitatively also. I look at the slope, that gives me d I by d e, I calculate d e by d I, and with an experimental error it has to settle there. Here it says infinity, slope is 0, inverse of slope is infinity. Here slope is more or less 0, inverse of slope has to be very large number or infinity, but we normally expect that to settle at the real axis. We say if I apply a very slow sinusoidal current, sinusoidal potential, current has to follow this. Okay. That will happen when this behaves like a resistor. If you have a capacitor, regardless of how low this frequency is, the phase will always be 90 degree. If you have a resistor or a combination which reduces to a resistor, then it will settle at the real axis, the phase will be 0, or within noise level it will be 0. Okay. This curve does not tell us that this system will give you a capacitor like behavior. That means, the potential current diagram does not tell us, or current potential diagram does not tell us that low frequency impedance will show as a vertical line. Warburg impedance, for example, if I have a semi infinite diffusion, current will be close to 0, the slope will be close to, not current will be close to 0, at OCP current will be 0, slope also will be close to 0. Warburg impedance goes like this. As far as I can see, it is going to be 45 degree line, As you go to lower frequencies, the magnitude becomes higher and higher, it tends towards infinity as omega tends to 0. Phase does not tend to 0, as you can see from this line. Likewise, here the phase actually goes towards 90 degree. Okay. So, that is modeled using this circuit. Solution resistance is there. B here corresponds to barrier film capacitance. This RB is the film resistance. So, we assume there is a solution resistance, there is a film, the film offers a capacitance as well as a, it is not a conductor. So, it is a semiconductor, it has a capacitance, it has a resistance to migration of the vacancies and interstitials. This C0 is called Faraday's pseudo capacitance. Okay. This can be visualized as the variation of film thickness with potential, that is dL by dE. This surface charge is given by the subscript Sc. This model predicts that you will have two elements, resistance and inductance, to represent the negative surface charge near the oxide solution interface, meaning near this place you have more cation vacancies, lot of anions are present. So, you have more negative charge. Of course, you have more positive charge here if you assume that anion vacancies are produced here, cation vacancies are consumed. So, mostly it is filled with cations and they are getting taken up, vacancies are taken up. If I understand correctly, the journal article says that this represents a negative surface charge near the oxide solution interface. This circuit is used to model. Of course, these elements are related to the diffusion and kinetic parameter values. And if you use this circuit, it will predict, if you go to low frequency, what happens is at low frequency no current will go through this. This offers 0 resistance, this offers some finite resistance together, but this offers the maximum resistance to low frequency. So, it is going to behave like a capacitor with a resistance offset. This is solution resistance, this offers an offset here and then it will predict that it will go vertically up. Another situation where you have niobium in sodium hydroxide, concentrated sodium hydroxide and at high concentration, high temperature, comes like this. The potential and current, if I take a potential and polarization, it will go like this. In the passive region, they see curve coming and settling here. This region goes up. Of course, some of the example actually it goes here and then settles, but they are modeling only the part where it goes up. It is possible to model this also, fairly complex expression accounting for niobium becoming, I think niobium 4 plus or 2 plus, I do not remember now, in the lattice, I am sorry, not nickel, niobium, and then 5 plus going into solution, 4 plus going into solution, or it could be 2 plus if I. There is another theory, it is called anion incorporation within the oxide film. This is proposed by Disheng Kong. So, the surface charge model says this is the behavior, of course, with a capacitance here. Okay. I am sorry, this is the model proposed, anion incorporation model. This is the surface charge model. Okay. The surface charge model, we have seen that you have a C0 here, which accounts for variation of film thickness with respect to the potential. Another interpretation of the data is this. Okay. This is usually seen when you have fluoride ion. We do not see this behavior, I mean this inductive loop. Usually we see this when you have fluoride ion, F minus ion. F minus ion is going to be very small, okay, and that similar size as oxygen anion. So, the interpretation is in different situations Okay, again this is not drawn to scale, they are considering only one film, not multiple layers. You can have anion here is fluoride ion. Most cases the anion will come, it will not even go through the film, some of it may occupy the location of oxide vacancies, but that is it, it is not going to move in. May be incorporated in the film solution interface near that location, in the film it may get incorporated, that is it, not significant movement of this. If the anion movement is smaller than the oxygen anion movement, oxide ion movement, then concentration of the anion is going to look little high here, decreases and then it is 0. If that is comparable, then concentration will be non-zero, mostly it is going to be here, but near the film solution interface it will be little high, but this is going to be non-zero, slightly above 0. In case the anion movement is faster than the movement of oxide ion, they expect that it will move in and it will accumulate here, because anion is present to a large level, fluoride ion may be present to a large level here, you will still see a slope here, to say concentration will be little higher near the interface and lower here, but then it preferentially moves in this direction, because we have applied a positive potential, the negative ion will move and it will move faster than oxide ions. So, it causes an accumulation. Now, if you apply an AC potential, high frequency it can't keep up with that, it will not just move with the potential. At low frequency it is possible these anions will move to this side and this side, and they are moving faster than what you would expect with the oxide anion. And his proposal is that this can cause the behavior where low frequency it goes up. So, they take part of the surface charge model, they incorporate diffusivity here. This diffusivity or the mass transfer relates to the movement of this fluoride ion, which are incorporated in the film. Okay. So, basically at low frequencies, if you see a vertical line at low frequency and high potential, if you see a vertical line in this complex plane plot and you see a mid frequency inductive loop, point defect model does not explain that. Of course, this is seen in a very few restricted cases, usually with Wahl metals, usually with acidic fluoride medium.
So, this is only for high DC potentials, right?
Yeah, high DC potentials. Inductive loop may come at low DC potentials, but it can be a kinetic limited case. For example, I can get data like this, we can explain all those within the framework of mechanistic analysis. If you have a high rotational speed for the electrode, then you do not have to worry about mass transfer limitations, and you might still see this. We have seen this before, right? You can explain an inductive loop like this with kinetics. Of course, you have to see whether it is realistic to explain for that particular case. See, impedance spectroscopy gives you an idea about the system, but it does not tell you everything about the system. You will have to use other tools to augment this information. It is like saying if you do UV visible spectroscopy, if I tell you at 500 nanometer wavelength you have 0.3 absorbance, you can't tell anything about it. It can come from an inorganic salt, it can come from an organic dye. You will have to use other techniques to have an idea, and you can use this also, UV visible spectroscopy also. If you already know what is going to be in there, it is okay. If I give you an unknown solution, very dilute concentration, you put it into UV visible and you measure at one frequency or one wavelength, you really can't say anything about it. You can just say it is pure water or contaminated, that is all you can probably say. Even if you get over wavelength, you may not be able to say much about this unless you identify few signatures. You will have to use other techniques to identify what are the compounds present, then to know the concentrations at different samples you can use this. Okay. So, I will probably stop with this. So, in summary, when a film is present on surface and when you are looking at the impedance spectra, it is not that easy to give a model for that. When it is for passive conditions, you can use point defect model, okay, that appears to predict lot of these features successfully and explain the phenomena successfully. And some cases you may have to use variants of this like surface charge model and anion incorporation model. These are alternate explanations, right? SE and AM are complementary, meaning both are aiming to interpret the same data. So, it is possible that the thickness varies with potential and that explains it. It is possible that anion is incorporated and that explains it. From my point of view, I can't really tell which is the better model, okay, but these are proposed. So, I want you to be aware of this. Okay. What we will see next Tuesday is few examples of what is published in literature. Okay. We will stop here today.